Welcome to homework.
Part A of the problem, with the temperature T is equal to 98.6 Fahrenheit, which is equal to 37 degrees Celsius, that is 310 Kelvin. We use the Vane's law and find the wavelength that corresponds to spectral radius maximum, that is lambda max is equal to 289.8 micrometer Kelvin divided by 310 Kelvin. This gives us lambda max of 9.35 micrometer. Part B of the problem, with the lambda that is at 9.35 micrometer and T which is at 310 Kelvin, the spectral radius is given by S function of lambda, that is 2 pi times speed of light square h divided by lambda 5 or 1 over e to the power hc over lambda kt minus 1. Then in next step we substitute the values for Planck constant hc and the temperature. Temperature we have here T is 310 Kelvin. After substituting those values, we get S of a lambda to be 3.688 times 10 to the power 7 watts per meter cube. For a small range of wavelength, the radiated power may be approximated as P is equal to S of lambda times A times delta lambda. This will be 3.688 times 10 to the power 7 times 4 times 10 to the power minus 4 times 10 to the power minus 9 meter. This gives us 1.475 times 10 to the power minus 5 watts. Part C of the problem, the energy carried by each photon is E is equal to hf, that is hc divided by lambda. Then we substitute the values for h and c, which is a constant, divided by lambda, which is 9.35 times 10 to the power minus 6 meter. This gives us a 2.1246 times 10 to the power minus 20 joules. Writing P in terms of P is equal to dN over dt times E, we find the rate to be dN over dt rate is P over E, that is 1.475 times 10 to the power minus 5 watts divided by 2.1246 times 10 to the power minus 20 joules. This gives us a rate to be 6.94 times 10 to the power 14 photons per second. Part D of the problem, if lambda is 500 nanometer and T is 310 Kelvin, the spectral radius, again using the formula that we wrote before, is 5.95 times 10 to the power minus 25 watts per meter cube. We will use the formula that we used previously for this S of a lambda and substitute the value of a lambda 500 nanometer, and then we obtain the result of 5.95 times 10 to the power minus 25 watts per meter cube. Part E of the problem, the energy carried out by each photon is then given by E is equal to hf, that is E is equal to hf, that is hc divided by lambda. This is 6.626 times 10 to the power minus 34 times 2.998 times 10 to the power 8 meter per second divided by lambda, that is 500 nanometers. That means converting into meters, that's minus 9 meters. This gives us E to be 3.97 times 10 to the power minus 19 joules. The corresponding photon emission rate will be then dN divided by dt is P divided by E. We substitute the values for P and E. P we have is 2.38 times 10 to the power minus 5 watts over 3.97 times 10 to the power minus 19 joules. This gives us 5.9 times 10 to the power minus 19 photons per second.